How can we get this modern photo on this classic Mac? Along the way, we'll learn about pixels and algorithms. So our goal is to take a modern photo and display it on the original Mac. The first Mac model was called the Mac 128K, and it came out in 1984. Now, it was very limited in its display capabilities. It only had a 9-inch screen with a tiny resolution, 512 by 342, and it could only display black and white. And I don't even mean grays. I mean literally just the colors black and white, just two colors. No in-between shades between black and white. So we also need to think about the software side. Software on the original Macintosh that came out in 1984 for displaying graphics was very limited. There wasn't a large software library. One of the first apps was called MacPaint. MacPaint was a revolutionary drawing app that democratized making art on computers. It also operated in that black and white environment. So we're going to need to make our modern photo work within MacPaint because MacPaint was one of the only graphic software available on the original Macintosh. How are we going to take our color photo and turn it into something displayable on the original Macintosh? We'll need a way of going from color to black and white. So we could do an intermediary step of first going to grayscale. Grayscale just means we have shades of gray between black and white. And then what we could do is decide, well, if a pixel is more like black, so if it's a darker gray, we'll make it black. And if a pixel is more like white, so it's a lighter gray, we'll make it white. We would call that the threshold effect. We just decide at some point, like the midpoint, we might decide that 50% shade of gray, 50% between black and white will be the midpoint. Anything more than 50% towards black will become black. Anything less will become white. Wouldn't look that good. This is what the threshold effect would look like on this image. There is a better way. That's why dithering algorithms were invented. So I want to talk about one particular dithering algorithm, but I want to give credit to its inventor, Bill Atkinson. He was a genius software developer who worked at Apple in the 1980s, developed many things that you're probably familiar with, including the graphics subsystem for the original Macintosh called QuickDraw. He developed MacPaint, the aforementioned painting app, one of the first mouse-based graphics app that was widely distributed, really set the paradigm of how we interact with graphics on the computer going all the way to today. And he also created HyperCard, which was a hypertext system that was pre the web. You operated just on one computer. I enjoyed using it a lot as a kid and was very innovative for the time. And if it had become a network system, it might have become what the web is today. So really a great software developer who unfortunately just passed away last year with a lot of accomplishments to his name, including inventing a dithering algorithm, which is relevant to what we're doing today, called Atkinson Dithering, named after him. He wasn't the first to come up with this type of dithering algorithm, and we're going to talk about what they are. They're in a category called error diffusion dithering algorithms, and the most well-known one was actually invented 8 years earlier in 1976 by Floyd Steinberg. Those are two different people who worked together. And his algorithm is another version of the same concept from Floyd Steinberg, but we're going to specifically talk about Atkinson's algorithm because it was used a lot, as you might imagine, on the original Macintosh. And I read in this book called Inside MacPaint, which is a very rare book, that he worked on digitizers for the early Macintosh as well. Digitizers kind of like a scanner, way of taking real-world objects and putting them inside an early Macintosh. And so they needed some way of taking this real-world image data and converting it into black and white. And so I imagine he invented Atkinson Dithering for those digitizer projects that he was working on. With Atkinson Dithering and error diffusion dithering algorithms in general, we can do a lot better than we were doing with threshold. So we're still going to start by converting to grayscale, but then we're going to find ways to smooth out the transition to pure black and white. You can really see in this dithered image the contours of the original image. In fact, it looks like a grayscale image, even though it's just composed of black and white pixels. It's really quite an amazing effect. Let's walk through step by step how we're getting this kind of smoothing where we can still see the contours of the different parts of the original image instead of seeing that harshness that we saw in threshold. So here are the steps of all error diffusion dithering algorithms, including Atkinson dithering. The first thing we're going to do, and we're going to do this for every pixel in the entire image, is we're going to choose which of our output colors it's closer to. And by the way, this doesn't have to just be with black and white. If you've ever used a GIF image file format and you've converted, let's say, your JPEG that was millions of colors to a GIF, GIF is limited to just a color palette of, I think it's 256 colors. And in GIF, we still end up oftentimes with images that look great, like they're full of rich color detail because of dithering algorithms. Dithering algorithms are used all the time when creating GIFs. So we can use dithering algorithms with any number of colors, but it's very simple here because we're just going to be working with black and white. So all we need to decide is for a given pixel that's in our grayscale image, is it closer to black or closer to white? And usually we're dealing with 8-bit grayscale, meaning that every pixel is represented by one byte that represents up to 256 different shades of gray, 0 through 255. 255 will typically be white, and 0 will typically be black. And then we have all these shades where the darker ones are closer to 0, and the lighter grays are closer to 255. So if we have, let's say, a pixel that is the number 75, well, 75 is closer to 0 than it is to 255. So we would say that it's closer to black, which is 0, than it is to white, which is 255. So we would choose black in that case for a 75 grayscale. Okay, once we've figured out which color it's closer to, then we find the difference between the color and the original pixel. So in this case, let's do the 75 example. We originally had level 75, now we're going to 0. The difference between the two, between 0 and 75, is obviously 75. So that's what we call the error. That's the distance between what we ultimately made the pixel and what it originally was. How far were we off when we made that choice of color? And then the last step is we're going to diffuse some of that error to surrounding pixels. That's how you get this kind of smoothing effect with error diffusion dithering algorithms, because you're taking how far you were off and saying, okay, let's use some of that offness on the pixels around us so that that offness kind of disperses and it isn't just lost. It's not just lost information. In threshold, it was totally just lost information. We just said, are you black or are you white? And we forgot about the richness of how far you were between black and white. But with error diffusion, we're able to take that data and reuse it to affect other pixels that might actually eventually lead them to a threshold where some that would have been black in threshold are actually going to become white, and some that would have been white are going to become black because error from other ones is distributing and affecting them. Okay, if we look at it up close, you can really see the effect very well here, and you can see, as I described it, a kind of smoothing effect, unlike threshold. You can really see the details in the original image that got lost in the blob that was threshold, where we just had a blob of black pixels in the hair, for example. Here we have that smoothing effect because the hair wasn't perfectly black. The hair was shades of gray that were close to black. And so what we ended up using that information for was to affect other hair pixels and actually lighten them a little bit with that error, saying, hey, pixel that's near me, don't go all the way black. I'm going to give you enough of my error that you're going to end up going white. And then we end up with still a density where pixels that are more close together look like a darker shade. More black pixels close together look like a darker shade of gray, and more white pixels close together look like a lighter shade of gray. But it's coming from somewhere real from the original image and that error. So how does Atkinson dithering specifically, if you look at the table on the right here, Atkinson dithering takes 1/8 of the error for each pixel and distributes it to 6 surrounding pixels. So ultimately, we only distribute 6/8 or 3/4 of the original error of each pixel, which is different than some other error diffusion algorithms, which actually will distribute all of the error. So that's one actual interesting difference with Atkinson. Another interesting difference is it's a uniform amount of error that gets distributed to the 6 other pixels. It's always 1/8 with Atkinson. With some of the other error diffusion algorithms, that varies quite a bit to which pixel how much error goes relative to the original pixel. Okay, Let's actually walk through the math here. So here I have 15 grayscale pixels, and the one that we're going to focus on is the one that's highlighted in red here that has the original grayscale value of 53. And remember that black is 0 and white is 255. We're dealing with 1 byte for each pixel, therefore 256 different levels of gray. Okay, so we're going to look at our table. Our table helps indicate to us, relative to the original pixel, which other pixels are we going to be affecting and distributing that eighth of the error to. How are we going to calculate the error? Well, our original pixel was 53. 53 is obviously closest to black at 0, much closer to black than it is to white at 255. So we just subtract the difference to get the difference, and the difference is 53, obviously. 53 minus 0 is 53. And then how much are we going to diffuse? Well, in Atkinson Dithering, we diffuse 1/8, so we take 53 divided by 8, and using integer division, where we cut off the decimal point, we end up with 6. So we're going to end up, our diffusion amount is going to be 6 that we distribute to 6 surrounding pixels. Okay, what does that look like? We find those 6 surrounding pixels as indicated by the table to the original, which is x, by the way, in the table, and we add 6 to their grayscale values. Okay, once we add 6, and I've actually made the change here, you can see they're actually getting lighter. Why are they getting lighter? Because the original pixel, the 53, was lighter than black. It wasn't all the way at black. It was a dark gray. And so it makes sense that we're affecting pixels around it, lightening them, so that some of them will eventually cross a threshold perhaps and become white, right? Instead of being maybe set to black. And that is where we're getting that smoothing effect from, by using that error to affect other pixels. Okay, and we would keep doing this for all the pixels. So then we go to the next one. You go usually from top left to bottom right when you do an error diffusion dithering algorithm, although there are some versions of it that kind of zigzag. But we go to the next one, and then we again would be figuring out, is it closer to black or white, calculating the error, and then distributing the error. And I've drawn arrows here to indicate which 6 pixels we would then be distributing the error to. So that's Atkinson Dithering in a snapshot. But we're not done yet. We might have our image as a black and white image now, but we need to convert it into a file format that our original Mac can read. And remember, the only graphic software it really had was MacPaint. Okay, well, how does MacPaint work? I'm not going to go in all the details of the MacPaint file format. It's actually not a super complicated file format, but I'll tell you 2 important points. One is that the way MacPaint represents pixels is using individual bits. So if you remember from computer science, there's 8 bits in a byte. So every byte actually accounts for 8 pixels. And if a pixel is supposed to be black, then the bit will be 1. And if the pixel is supposed to be white, then the bit will be 0. Okay, that's simple enough. And I'll show you an example of that in a second. The other thing we do in the MacPaint file format is we use a compression scheme called run length encoding. And run length encoding just says, instead of repeating myself a lot, if I'm going to do the same thing over and over again, I'll just tell you I'm going to repeat it. So if I was going to say to you, I'm going to repeat the word hi to you 8 times. Hi, 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 hi. Was that 8? I hope it was 8. I could instead say, hey, here's hi times 8. Here's 8 highs. Isn't it easier and take up less space for me to say, here's 8 highs, than to literally say the word hi 8 times? So it's a simple form of compression. If I know something's going to be repeated, I just say, I'm going to repeat this thing multiple times instead of actually repeating it multiple times. Okay, let's first look at the going from pixels to bits. So on the left here, we have an 8x8 image that has mostly white pixels, but it has some black pixels, kind of writes out the word hi. What would that look like as 1s and 0s, where 1s represent black and 0s represent white? Well, it would look like the right image here. Pretty simple. You can see the correspondence very easily, right? And we could actually therefore then encode this entire image using just 8 bytes, because if I can do every row of the image with 8 bits, and there are 8 rows, I need only 8 bytes to encode the whole thing. Okay, what would that look like as bytes? So here all I've done is I've taken the 8 bits and I've converted them into decimal from binary. So we see here then 8 bytes of integer values, 0, 74, 74, 122, etc. Okay, so that's going from pixels to bits, which we can then represent using bytes. What about the encryption scheme? So here we're using pack bits, which is a standard way that the original Mac used to compress bytes. So the way pack bits works is not super important for understanding the overall idea, but I will go through it briefly. So if a number is supposed to just not repeat that many times, then we call it literal bytes. And so what we first have is an indicator saying how many literal bytes are there going to be. And if you get a value between 0 and 127, then it means that there's going to be that plus 1 number of literal bytes that follow. If, however, we want to actually say hi 8 times, or here this thing is going to repeat itself, we give a number between 129 and 255. This is all because this fits in 1 byte, and 1 byte can represent the numbers between 0 and 255. And then that means that the next byte is going to repeat itself 257 minus that number of times. So for example, if I give the number 255, 257 minus 255 is 2, so that means the next byte is going to repeat 2 times. And then 128 is just skipped altogether. It's just a marker of an ending of something. So, okay, so let's take our original 8 bytes for representing our image of the word hi and use pack bits to convert it. So we started with the number 0. So we have to first say there's going to be a 0. And that would mean 0 plus 1 is 1 literal bytes follow. And then we have 1 0 after that. Then we have the number 255. What does that mean? That means 257 minus 255 is 2, which means the number 74 is going to repeat twice. The byte 74 is going to repeat twice. Then another 0, meaning that the next byte is a literal. So 122 is a literal again. Then we have 254 because 257 minus 254 is 3. So that means the byte 74 is going to repeat 3 times. And then we have a 0 for another 0 right after that, one more 0 literal. Now you'll notice here, this is an interesting example because actually using pack bits, it ends up being more bytes using what was supposed to be in compression than it is not using pack bits. So this actually didn't save us anything. This scheme actually cost us room. Now, the way that I described how it works here is the general gist of it. The MacPaint format also has some limitations around how many bytes can fit on each line, and it actually ran pack bits on a line-by-line basis. But regardless of that, let me show you a better example, because this is one where pack bytes actually saves us some room, and I won't walk through step-by-step how this works. If you want to prove it to yourself, you can pause the video here and look at it. But this takes an original piece of data that's 24 bytes, and when we run it through pack bits, we end up with just 15 bytes. So this compression works. We saved 9 bytes, which is a significant amount. That's like 40% of the original data we saved. So that's pretty nice compression, actually. And run length encoding is something that real compression formats, I'm sure you've used compression formats before, like zip or gzip or something like that, use as part of their algorithms. It's not the only part of the algorithm, but it's a significant part of many compression algorithms is something like this. So this was a primitive form of compression that was pretty fast to execute on the early Macintosh that was included in the MacPaint file format. Okay, to actually take our original image and convert it to MacPaint, we need software that does this, that does the dithering and then converts the MacPaint file format. I happen to write software called Retro Dither, so I'll show you now how that software can be used to convert a modern image into MacPaint file format, including dithering. So here we are in Retro Dither. All we have to do is drag an image onto Retro Dither. It'll convert it to black and white. The default dithering algorithm is Atkinson Dithering. So that's what we're going to use here. And then I'll just click the export button to go to MacPaint. and we can then save it, this beach view, in the MacPaint file format that actually gets encoded automatically in Retro Dither into what's called Mac binary, because of some details about how the original Macintosh used resource forks versus the modern Macintosh, which does not, but that's beyond the scope of our video. So anyway, this is a file that we'll be able to open on the original Macintosh. And it's as easy as that. Okay, now that we have a MacPaint file, we need to somehow get it onto our classic Mac. Now, that Mac I showed you at the beginning, it's actually, I'm going to cheat a little bit here. It's actually been upgraded to be a Mac Plus. So you could do that. You could take a Mac 128K or a Mac 512K, and you could upgrade it to a Mac Plus, which was a computer that came out in 1986. The reason we need actually a Mac Plus to do this easily is that the Mac Plus has a SCSI port on the back. The original Mac used 400K disks. The Mac 512K and the Mac Plus actually used 800K disks. I have a USB floppy drive, but you can't make 800K or 400K disks on a modern USB floppy drive. There is some other software called, I think it's called Greaseweasel, and there's other ways of making those disks, but I don't have that equipment. So I'm going to cheat a little bit. We're going to use a Mac Plus. And a Mac Plus also, because it has a SCSI port, is able to hook up to some more modern devices that will allow us to transfer data from our modern Mac to the Mac Plus. And I should also mention, on whatever disk we're using, we're going to be using the HFS file system, which is a file system that is no longer supported by modern Mac OS. It never was really supported by Windows without extensions. And so we're also going to need special software for this step as well. So we need to somehow get our MacPaint image onto a device that can hook up to my Mac Plus through its SCSI port. Luckily, there is such a device, and there's actually multiple. There's one called Zulu SCSI, there's one called Floppy MU. I'm using one today that's called Blue SCSI. And Blue SCSI will take an HFS disk image, that's a disk image in the format that the original Macs understand, and allow you to boot off of it from the SCSI port as if it was an external hard drive. And it runs on a micro SD card, so it's really fast and reliable, and it's actually a really, really great device. I highly recommend it. But we need some way of getting the MacPaint image onto a disk image that can go on the Blue SCSI. So just like I wrote Retro Dither for converting to MacPaint format, I also wrote some software called Sector that allows us to take files and put them on HFS disk images that can go onto the Blue SCSI. So I will show you that now. We'll take the MacPaint file and we'll put it onto the disk image that we can then put onto the Blue SCSI and hook up to the original Mac. Okay, I have my Blue SCSI hooked up over USB to my modern Mac. On the Blue SCSI, we have my HFS image that I'm going to open by dragging over to Sector. I have a bunch of system folders on here. I also have MacPaint, of course. I'm going to drag in the beach view file, which we exported from Retro Dither. It was encoded in Mac binary, which Sector knows how to automatically convert back into a regular file, which it just did. We now have the beach view, hopefully working MacPaint file on our HFS image that is in our Blue SCSI that we can now hook up to our Mac Plus. And now we have it, the real moment of truth. We're going to turn on our classic Mac with our Blue SCSI hooked up behind it. And we're going to see, do we actually get beach view back here on an early Macintosh? Now, to be fair, this upgraded early Mac has seen better days. It's not the best condition Mac Plus. Probably needs some capacitors to be recapped. It probably needs some adjustments to its screen, but hopefully it'll boot up and be enough to at least let us prove that this all worked. Okay, we're here in our HD. I see beach view. There's beach view. And let's open it up. And there it is. Wow, beautiful. Should we zoom in a little bit? Pretty amazing. We have our modern photo on our classic Mac. I will include links in the show notes to Sector as well as to Retro Dither if you want to buy them on the Mac App Store. The code for doing this, there's actually a Python version, it's command line version, not as friendly, but it comes bundled in my book. In Chapter 3 of Computer Science from Scratch, I go over how all this works in a lot more detail than I did in this video. And I show you step by step how we build the software behind Retro Dither. And I explain a lot about how the MacPaint file format works and how dithering works. And we also have all of that code online on GitHub. So I'm going to put a link to that in the show notes. If you don't want to spend the $2 to buy Retro Dither, you can use the command line Python version from the book. And if you don't want to get Sector to take images and put them on HFS disk images for Blue SCSI, there's an older set of command line utilities called HFS utils that I actually built on top of. They're open source, just like Sector's open source, and you can go and build HFS utils yourself. So I will put a link to HFS utils as well in the show notes. But I hope you enjoyed this video. I hope you learned a lot about how images can work on the original Macintosh. Hope you learned a little bit about dithering algorithms and run length encoding and file formats and stuff like that. And I'll see you in the next one.